Hi, my name is John Krockmalny, and I've developed these video presentations to orient PLC learners to automation technology now being used in industrial, commercial, and residential applications. This presentation will be exploring the PLC outputs and how they relate to the PLC control technology. There will be 4 learning outcomes associated with this presentation. Number 1, describe the voltages related to PLC output modules. Number 2, identify dry contacts in the PLC output modules. Number 3, explain PLC output module operation. And number 4, identify components related to Programmable Logic Controller analog outputs. Remembering previous presentations, the outputs of a PLC receive their commands from the Programmable Logic Controller processor, or CPU. These commands are given after the processor analyzes the input conditions and then makes decisions to control those environments. All PLCs have power supplies, processors, inputs, and output modules. Usually, 120 volts AC is used to supply PLC assembly power. The components making up the PLC assembly operate on 20 volts DC. It is this 20 volts DC that powers and enables inter-module communications. Also remember that there are other voltages being supplied to PLC modules for their operation as well. Using this type of PLC architecture, PLC controls can make use of lower voltages and currents to make decisions and gate higher voltages and currents to affect changes in the controlled environment. In this graphic, another voltage, not one coming from the Programmable Logic Controller itself, provides the power to the input devices. Input termination screws become electrically active and allows for an LED to illuminate, indicating voltage present on those screw terminals. Output modules operate in comparative ways with input modules. Output terminal screws will be identified with an O, which stands for output. Some PLCs, like the Omron Zen controller, identify their output screw terminals with the letter Q. Like the input modules, the PLC output module will also have diagnostic LEDs that technicians can refer to for output device status. A separate power needs to be applied to the output module to control output devices. This power is often 120 volts AC and controls relays, contactors, light bulbs, and more. It is these devices that operate motors, lighting systems, electric resistance heaters, and more digital devices. Other voltages could be used here as well. For example, if photovoltaics are being used, perhaps 12 volts DC may be the supplied power source. A system designer could also use 24 volts DC or 24 volts AC power, depending upon customer requirements. The term dry contacts are identified as ones that have their power coming from a source outside of the PLC assembly. The dry contacts will have the voltage being sent to it from this other source. These dry contacts open and close by a command coming from the Programmable Logic Controller processor. In this graphic, we see a control circuit made up utilizing a 5-volt DC switch, S-0. This switch controls a circuit with a solenoid coil, which affects a set of normally open contacts identified as C-0. The condition of the contacts C-0 determine if the R1 load operates. In this graphic, the switch in the PLC processor S-0 is powered with a 5-volt DC supply. With the switch S0 open, the solenoid coil in the output module is not energized. In this condition, the R1 load is off. With the PLC processor closing the S-0 switch, 5 volts DC initiates a current that energizes the solenoid coil C-0, resulting in the closing of the normally open contacts associated with C-0 contacts. This then allows the output module's supplied voltage, in this case 120 volts AC, to power the R-1 load. Notice that this load is wired to the output module screw terminals numbered 0. For the PLC programming purposes, the address for this load becomes O:0. The O is an indicator for an output device, and 0 is the indicator of the screw terminal the load is wired to. Notice also that the diagnostic LEDs located at the top of the output module illuminates, indicating the dry contact of C-0 status. In this graphic, we can see additional loads wired to terminals number 1, 2, and 3. The PLC addresses for these loads become O-1, O-2, and O-3. The diagnostic LEDs associated with these circuits will also display status when active. Similar to input modules reporting to the PLC processor, the processor communicates with the output module using a registry. In this example, switch S-0 in the processor is open and therefore de-energizing the solenoid associated with the screw terminal marked 0. For this condition, a 0 is placed in the appropriate output data box. Here we can see switch S-0 in a closed condition, which energizes the solenoid coil located in the output module, and thus closing the normally open dry contacts marks C-0. This now closed contact gates the 120 volt AC current to the R1 load, causing it to operate. Notice that when the S0 switch is closed, the output data box changes its value to a 1. Also notice that the diagnostic LEDs identified as 0 also become illuminated. Analog logic involves actual values instead of a just on and off condition. Applying the use of an air damper to this analog logic, the damper could be closed, 100% open, or perhaps open halfway, 50% open. A control signal could be sent to the damper motor for a desired open condition. Analog output devices such as valves and dampers are referred to as actuators and can be controlled to any position from fully closed to fully open. The actuator controlling the position of the dampers is located directly on the damper assembly. This actuator will take a control signal originating from the PLC analog output module for its positioning. There are usually two voltages offered to actuators. In this example, 24 volt DC is sent to the actuator motor for its operational power. The position of the damper is determined from a control signal originating from the Programmable Logic Controller output module. In this graphic, a power supply, independent from the Programmable Logic Controller's power supply, provides power to both the actuator motor and the PLC analog output module. The processor commands the actuator position by assigning a value of the control signal. The control signal originates in the processor and is sent to the actuator from the analog output screw terminal marked 0. For programming purposes, the address becomes AO-0. AO stands for analog output. 0 stands for the analog output screw terminal the actuator is wired to. Setting up a matrix for the analog output module, we can send a control signal in milliamps to control the actuator. Sending a 4 milliamp signal closes the actuator. Sending 20 milliamps fully opens it. By sending a control signal of 12 milliamps, the actuator achieves a 50% open position. Notice that in this example, we can drive the actuator from open to close and any value between using a milliamp signal. In this example, we can drive the same actuator from an open to a closed position. It would be safe to say that all programmable logic controllers will have outputs associated with their architecture. As previously stated, they all differ in size and complexity, but mostly they do the same thing. They look at an environment and try to control that environment according to set procedures.